All right, welcome. Today, we're going to jump into one of my favorite tools in all of digital logic. We're going to break down the Carnot map and show you how it turns really messy algebra into, believe it or not, a simple visual puzzle. Let's get right into it.
So, picture this. You're designing a digital circuit, and you're staring down this monster of a Boolean expression. Your goal? Simplify it. You need to use the fewest logic gates you possibly can to make your circuit cheaper, faster, and just more efficient. Now, you could try to fight it out with Boolean algebra rules, but trust me, that's a long road. It's tedious, and it's so easy to make one tiny mistake that messes the whole thing up.
Exactly. You look at something that complicated and you just have to think, come on, there has to be a better way, a shortcut, right? Well, the answer is a huge yes, and it's actually pretty cool to look at.
And that brings us to the hero of our story today, the Carnot map, or as everyone calls it, the K-map. It's this brilliant graphical method that totally plays to the strengths of the human brain, our amazing ability to see patterns, to do all the heavy lifting for us. So what is it really? A K-map is basically just a grid of squares, where every single square represents one possible combination of your inputs. You take your function, and for every combination that makes it true, you put a 1 in its box. And just like that, you've created a picture of that super complex expression. Okay, now here is the secret sauce. Look closely at the numbering for the rows and columns. It goes 0, 0, 0, 1, 1, 1, then 1, 0. That's not a typo. That's called gray code, and it is the absolute magic that makes the K-map work. See, as you move from one square to any adjacent square, up, down, left or right, only one single bit ever changes. This is the key. It guarantees that any ones that are next to each other on the map are also logically next to each other, which is crucial for what we're about to do. And the process itself? It's honestly as easy as 1, 2, 3. First, you draw the right grid for your number of variables. Second, you plot your ones on the map. And third, this is the fun part, you draw loops around groups of ones to find the simple answer. Right, this step, grouping, this is where the visual magic happens. When you start spotting these patterns of adjacent ones, you're visually canceling out variables. You're simplifying the logic in a way that just feels so much more intuitive than pushing symbols around in an equation.
The rules of the game are pretty straightforward. You can only group the ones. Your groups have to be rectangles, and their size has to be a power of 2. So 2 squares, 4 squares, 8, and so on. Your main goal is to make the biggest groups you possibly can, and it's totally fine if the groups overlap. And here's my favorite rule. The map wraps around. You can group ones on the far left edge with ones on the far right, or the very top with the very bottom, just like Pac-Man zipping through one of those side tunnels.
Okay, let's look at a real example. Here's a 4-variable map, all filled in with ones. Right away, your brain is probably starting to see it, isn't it? You're seeing some potential rectangles. The game now is to cover every single one using the biggest groups you can find. Remember, you can reuse a 1 if it helps you make another big group.
And here's the payoff for making those big groups. It's simple. The bigger the group, the more simplification you get. A group of 2 ones gets rid of 1 variable. A group of 4 ones, that gets rid of 2 variables. A group of 8 knocks out 3. The bigger the loop, the simpler your answer.
And boom, this right here is the aha moment. This shows the real power. On the left, you've got these 4 different terms, which, when you add them all up, give you that long, ugly equation we started with. But look what happens when we spot that vertical group of 4 ones. Let's analyze it. Inside that group, as you go from top to bottom, what changes? The A and B variables flip around. Since they change, poof, they're gone. They're eliminated. Now, what stays the same for that entire group? Well, C is always 1, and D is always 1. So that whole complicated mess just simplifies down to one beautiful term, CD. That's it. That's the magic.
Okay, but the K-map actually has a few more tricks up its sleeve. You can think of them as power-ups that help us get even better answers. The first power-up is the don't care condition. We mark it with an X. These show up for input combinations that should never, ever happen in our circuit, or situations where we just, well, we don't care what the output is. This gives us a strategic choice. You can treat an X like a 1 if it helps you draw a bigger rectangle, or you can just ignore it and pretend it's a 0. It's basically a wild card you can use to win the simplification game.
Check this out. On this map, we've got 2 ones that could make a small group of 2. But hey, look, right next to them are 2 don't care X's. By deciding to treat those x's as ones, we can suddenly draw a much bigger, much better group of 4. And as we just learned, that eliminates an extra variable. It's pure strategy.
You know, so far we've only been talking about grouping the ones. Doing that gives you what we call a sum of products expression. Think of a bunch of and terms all ORed together. But guess what? You can play the exact same game with the zeros. If you group the zeros, you get a totally different form called the product of sums, which is a bunch of OR terms all ANDed together. Both answers are correct, which just gives engineers more flexibility to pick whichever one is easier or cheaper to actually build.
So K-maps are just fantastic for 2, 3, maybe 4 variables. But what happens when things get even more complex? Let's take a quick look at how this awesome visual tool scales up and, where it starts to hit a wall.
So for a 5-variable problem, you suddenly need 32 squares. The way we handle that is by imagining 2 of our 4-variable maps stacked, like 2 floors of a building. One map is for when that 5th variable is 0, and the other is for when it's 1. You can then make groups that are kind of 3D, jumping between the 2 maps. And as you can probably guess, this is where our amazing 2D pattern spotting abilities start to get a little tricky.
And that brings up a really fascinating point, right? The K-map is a tool that is perfectly designed for the human visual system. It's not at all how a computer would think about this problem. So what happens when the problem gets too big and too complex for our brains to even visualize anymore?
Yeah, this quote pretty much says it all. Once you get past 5 or 6 variables, you're trying to visualize groups in a 4D hypercube or something even crazier, and our intuition just completely breaks down. The K-map is the perfect tool for human-sized problems, but it definitely has its limits.
And that leaves us with this final, really cool question to think about. How do you take this intuitive visual process of just seeing the answer and translate that into a step-by-step procedure that a computer can follow? Well, the answer involves some more advanced methods, like something called the Quine-McCluskey algorithm. It gets the same job done, but in a way that's perfect for a machine. And that is a story for another explainer.